Okay, the first part of the video, we are gonna discuss DC motor starters. Yeah, there are some special control and protection equipment required to operate DC motors properly, and the purposes of these equipments are as shown below. First, to protect the motor against damage due to short circuits, and then to protect the motor against long-term overloads, and to protect the motor against excessive starting currents. And as we know that the starting currents are one of the main problems that are faced by the operators of the motors, as the current can be multiple times higher than the rated current of the motor. And last one, to provide a convenient manner in which to control the operating speed of the motor. So how can we have this protection system, this electronic circuits that will do the jobs in protecting these motors from the previously mentioned potential problems. However, at the same time, we still have a convenient way, an effective way of controlling the motor, especially in terms of its speed. Okay, in order for a DC motor to function properly, it must be protected during the starting period. Yeah, at starting, the internal generated voltage EA, this EA is equal to 0. So if you apply this current here, terminal voltage, originally the motor doesn't have this starters, so it will the only resistance existing in the armature will be this armature resistance, which is a very low resistance. In this example here, it's says it's 0.05 ohms, so it's very low resistance, while the voltage that you apply can go in a range of hundreds of volts. Okay, right. So you can quickly calculate. Let's say you apply 100 volt, you've got 0.05 ohm resistance, so you will have something like 20 ampere currents, 20 amperes of current. So that's a very high of current. Okay, and if you apply higher voltage, then that can go even higher, and therefore we want to stop this from happening. And the way we do that is, later on we will discuss, is by adding this starting resistance, or starting resistors. Okay, so a solution to this is to insert a starting resistor in series with the armature to limit the current flow until EA can build up. Once the motor has started rotating, this voltage will go higher. It will become higher and higher as the speed is gaining. Therefore, the current, this armature current will be lower and lower, because that IA is equals to basically VT minus EA over RA. So as the internal generated voltage is getting higher and higher, IA will then decrease. Okay, so this is the solution. However, the resistor must be removed once the motor gains speed to prevent excessive loss. Because of the high current, if the resistor is still there, then it will then produce unnecessary or unwanted losses. Okay, so ideally, once the motor already reached some speed, then we want to remove these resistors from the circuit. Okay, how do we achieve that? We will see it in the next slide. Okay, sorry, before we come to the starting circuit for the motor, then let's have the quick introduction of the components of the parts that we are going to use in the motor starting circuit. Yeah. So first one, we have a fuse here. This is for current protection. If the current goes too high, then we want somehow to stop the current. Yeah, we can use this fuse. Yeah? The fuse has the current rating at which we want to limit the current at. Yeah? And then we have these push button switches. There are two types of them. First one is normally open, and the second one is normally closed. Okay, and then we have the relays, which consists of a coil and contacts. Yeah, and again this can be normally closed or normally open. Yeah, normally open is when this coil is not energized, you are not applying any current through it, then the contact will be open, and vice versa for the normally closed. And then the next one is we have a time delay relay. Yeah, this is again similar to the previous one, the relay, but it has a time delay, i.e. once you apply the current through the coil, and also once you energize the relay, it will take some time, a defined or a set time, before the contacts change state. Yeah, either from open to close or close to open, depending on the design. Okay, so again, the difference between this and the previous one is that it has some time delay. Yeah? While the previous one will the contacts will change state immediately, this one will change the its state after some time delay. Okay, and then we have here OL heater and OL contact. This is an overload protection system, detection. So when the overload is detected, then the contact will be open. This is a normally closed one that we use here. Yeah. Again, when the overload is detected, so it has some sensing here, then this contact will then be open. Yeah. Otherwise, under normal condition, the contacts are closed. Just to refresh our mind, this is how a relay works. Yeah. And yes, we've got this arm which is spring loaded. Okay, and if you see this animation, you can tell this is a normally open. Yeah? Relay. Yeah? When the coil is not energized, then the spring will pull. Yeah? The spring will pull the arm and make the contact open. Okay, and then if you apply current to this, or you apply voltage, then the coil will be energized, i.e. it will generate a magnetic field. That magnetic field will then pull the arm towards the magnet, and in doing so, making the contacts close. Okay, so again, this is a normally open relay. Okay, one common motor starting circuit is shown in the figure, yeah, on the right hand side here. Okay, if you see the circuit, the motor is actually here, yeah, I circle in red, and then if we look at the top part of the circuit, let's say if we close these two switches, then what will happen? If you look at the circuit around the motor, connecting with all the connection to the power supplies, yeah, on the top here, then we can see that this connection go through this resistors, we call it as R start, and also through this contacts, yeah? But the contacts, if you see the symbol, are normally open. So originally when we close these switches, these contacts are open, and then we have this contact amp, which is a part of a relay, yeah, while the other three that we here, the bottom ones, are part of time delay relay, yeah. So and the contact of this relay amp is also normally open, yeah, from the symbol, okay. You can, and on the right hand side of the motor we've got the overload protection, and then we have this again the contact of the relay amp. So the two contacts are connected to the same relay system, okay. And because the contacts are open, these contacts are open, so current cannot flow through the motor, yeah. And therefore even if we close the switches at the top, the motor will not start yet, okay. So then how do we start the motor? Okay, in this circuit, a series of time delay relays shut contact which remove each section of the starting resistor at approximately the correct time after power is applied to the motor. Okay, right. I think yeah, but before we get into that, so how do we start this motor? Yeah, how do we start this motor by using the starting circuit? We start the motor or the operation by pushing the start button, which is this one here, okay. This is the start button. So when you push, then this will be closed. Okay, when it's closed, then yeah, current can flow. Let's see how far it can go. Can it go actually go all the way around, yeah, in a loop? It will go, then it will go to the motor, and then here we've got a contact FL, yeah, which is a contact of field loss, and we need to see where is the coil of this. The coil of this FL is on the top here, yeah. And then if you look at the circuit, actually current can flow through this already, yeah. Because this two are resistances and this is inductance, and this itself will allow to current to flow, yeah. This is not contact, okay. So current can flow. It means that the sorry, this is actually a relay, this will be the coil of the relay, yeah. So it's just coil, so current can flow, and therefore the relay will be energized, yeah, because the current can flow through the coil, and therefore, yeah, then if you go to the here, therefore this contact will be closed. Okay, and this contact will be closed, so current can still flow. How about this overload contact? The overload contact is normally closed, yeah. So if it is not detecting overload, yeah, which is this one here, the sensing, then this will be closed. So because initially it's not, obviously it's not overloaded, current can then flow, and therefore after we push the start button, current can flow through this, yeah, and which means that the relay amp will be energized, and then it means that all the relay amp contacts will be closed, yeah? All the relay amp contacts will be closed. And where are these relay amp contacts? They are here, 1, 2, yeah, on the right hand side, and then at the bottom just below the push button, 3, and 1 underneath it, 4. Okay, so there are 4 contacts amp will be then closed. Okay, so when the contacts amp are closed, it means that now current can flow, yeah, because amp are already closed. The current will flow. If you look at the path near the motor, now current can flow through the contact, the first contact amp, and then through the R start, and then through the motor, then goes back to the negative supply. Okay, and now what this means? This means that now the motor has got current to it, and torque will be induced, and the motor will start to rotate. Okay, so the motor will start to gain some speed, yeah, and then what will happen? What will happen is now all this current will have to go through the R start, yeah. You have to go through the R start, which means that even if the motor gains, if the high current is flowing, when you have a high load, you go high current, so there will be excessive load, yeah, excessive losses, sorry, because of this R start, yeah, the starting resistance. Okay, however, the mechanism in this starting circuit will have some improvement on this, yeah. If you look at this rung here, when the contact M is closed, current will flow through this, yeah, then it will then energize this time delay relay. So after some time delay, not immediately, but after some time delay, the contact of this time delay relay will be closed. Where is the contact of this? The contact is here. So after some time delay, and within that time delay, the motor has gained some speed, yeah. The speed of the motor has increased, and then this contact will be closed. When this contact is closed, yeah, current will flow mostly through this contact instead of this resistor. Okay, so this resistor will be bypassed, if you like. Current will flow through this contact and goes through the remaining of the starting resistor. Okay, so again, if I draw it, try to draw it more properly. I draw this one first. So after this one time delay, the current will flow through the time delay, first time delay relay contact, and then through the R start, like this. Okay. But then there is another contact of this the first time delay relay, which is this one. So this will be closed as well after the time delay. When this is closed, this will then activate the second time delay relay. Yeah. So after the second time delay, the associated time delay contacts will be closed, which are these two. Yeah, and I draw these two squares to indicate the second time delay contacts. So after the second time delay, this will be closed, and if you look at the path near the motor, now the current will flow through contact M, the first time delay contact, and the second time delay contact, and then the remaining of the resistors. So you can see the resistance of the starting resistors becomes less and less, yeah, as the motor gains speed. Okay, and by doing this, we are reducing the power loss due to the starting resistors that we introduce to protect the motor from the high inrush or high starting current. Okay, and then after that, you know, if you look at right at the bottom, then the second time delay contact will be closed, then the third time delay will be activated, and therefore the third time delay contact here will then be closed as well, and then eventually it means that the starting resistor will be effectively removed, yeah, from the circuit. Okay, and so the motor is operating as normal, as if the starting resistors were not there. Okay, so there are two things achieved by this mechanism. First, the starting resistors protect the motor from high starting current. Secondly, because of the nice feature of this mechanism, that the starting resistors can be removed, yeah, when the motor already running normally at some high speed. Okay, again, you press the start button, then it operates the M relays, yeah, and then the first time delay will kick in. Okay, on this slide, we're going to have a look at the motor protection. Yeah. Again, here is the same circuit as we've seen in the previous slide. Okay, so the first protection is against the field loss. Yeah, field loss is a condition where the magnetic field is disappeared. Yeah? It stops, which can cause what is called as runaway. Yeah, here you see field loss may cause runaway. And if you remember, runaway is the condition where the motor keeps increasing in its speed, so the speeds getting higher and higher, which is potentially harmful to the motor. It can cause permanent mechanical damage to the motor. Yeah, so we want to avoid this. We don't want this to happen, and therefore we introduce this field loss protection. So what we have in here, we've got this field loss relay, yeah, FL. This is the coil, and the contact is here, yeah, on the right hand side here, slightly lower. So field loss is happening when somehow current stops flowing in this field circuit, yeah, of the motor. So when the current stops flowing in the field circuit of the motor. Okay, so when this current stops flowing, yeah, IF, somehow stop, maybe the what they call the field winding is broken, yeah, that's a possibility. So the current stops flowing, and therefore this relay will be de-energized. Yeah, it will be de-energized, and as the consequence, this contact will then turn open. Yeah, it was closed because it's normally closed, and the contact was the coil was energized. As soon as the coil, the field loss relay coil is de-energized, the contact will then open. When the contact is open, then this relay M will be de-energized, and therefore these two contacts will then be open as well. And when these two contacts are open, this motor will be disconnected from the power supply, and therefore basically we are switching off the motor. Yeah? So this is how we protect the motor from field loss. Okay, the other protection is from overload, yeah, which may cause some excessive heating to the motor. Okay, let's have a look. Where are the components and where are the parts that we use for this? Okay, now what we have here is what we call as the overload heater, OL. We can also say I think it's an overload relay, yeah, which is normally closed. So when this doesn't detect any overload, yeah, this contact will be closed. However, when it starts detecting overloading, yeah, the power gets too high, it will then cause this relay to be open. And similarly as before, when this one is open, then this relay M will be de-energized, and therefore again these two M relay contacts will be open as well, and therefore the motor will be switched off. Yeah, it will be disconnected from the supply and the motor is switched off. Okay, so this is the two protections for the motor, which any of these problems happening, i.e. overload or the field loss, the motor will then be switched off. Okay, now in this section we are going to look at speed controllers. The three different types of speed controllers that we are going to look at in this section. It's the Ward-Leonard, the two-quadrant SCR-based system, and lastly a four-quadrant SCR-based system. Okay, before we go into more details on the three different types of the motor controllers, let's have a look at this four-quadrant system first, yeah, which is going to be useful for us in the discussion later on. Right, this is a Cartesian system with four quadrants. So, and in the two axes, in the y-axis you've got the omega, which is the this is the omega, which is the speed of the machine, and then on the x-axis you've got the torque of the machine. Yeah, and then you've got four quadrants: 1, 2, 3, and 4. Okay, and then in each quadrant, then the torque and omega will interact differently. Okay, if you assume now the positive is direction of clockwise and negative is direction of counterclockwise. Yeah. So in the first quadrant, if you see that both of omega and the torque, both of them are positive. Okay? Both of them are positive. Okay, which means that both of them are going in the clockwise direction, which can be seen from these two arrows here, yeah, signifying the directions of the two quantities, the omega and the torque. And again, in this quadrant, the first quadrant, both of them are going in the same direction, which is clockwise. Okay, and then if you look at quadrant 3, the third quadrant, again, here omega is negative and the torque is also negative, and therefore both of them are in the counterclockwise direction. Yeah. And again, both of them are going in the same direction, although now it's counterclockwise rather than clockwise. Okay, now then if you look quadrants 2 and 4, yeah, in quadrant 2 omega is positive and torque is negative, therefore omega is in the clockwise direction, torque is in the counterclockwise direction, so they are going in the opposite directions. Okay, and in quadrant 4 torque is positive, speed is negative, so torque is in the torque is in the clockwise direction and speed is the counterclockwise direction. And again, similar to quadrant 2, in quadrant 4 they are going in the opposite direction. Now when the speed and torque are in the same direction, the machine is behaving as a motor. Yeah. So you've got the torque, and the torque will then accelerate the motor, and so that the machine, the rotor of the machine will rotate in the same direction, and that is the function or the behavior of a motor. Okay, but if they are going in the opposite directions, then it's behaving as a generator. Yeah, it will get some mechanical energy from the prime mover, which is causing it to rotate, but at the same time the motor will, the machine will produce the counter torque. Yeah, the torque that is in the opposite direction to the direction of the rotational speed. Okay, now let's have a look at the first speed controller, okay, DC motor speed controller. Okay, before the solid state electronic components became available, it was difficult to vary DC voltage, and as we will see from this system, what is called as the Ward-Leonard system, we are actually going to use extra, additional machines to control the speed of the DC motor that we have. Okay, and the diagram here, this is the DC motor that we want to control. Okay, so in this solution we are using a separate DC generator, which is this one here. Okay, the DC generator can be used to produce variable DC voltage output. Yeah. Okay, and this is what is called as the Ward-Leonard system, i.e. when you have a DC motor, you want to control its speed by using a separate DC generator. Yeah. Okay, and to operate this DC generator, we are using an AC motor, yeah, which is one here. So you can imagine, to control this DC motor, we use two extra machines, which are the DC generator and the three-phase motor. Yeah. Okay, the armature voltage of the motor, yeah, which is this voltage here, in this case, can be varied or can be controlled by varying the field current of the DC generator. Okay, for this DC generator, it has its own field circuit. Yeah, it's got where we can connect a resistor, a variable resistor, so that we can then adjust the field current of the DC generator by changing the field current IF. Yeah, we can then control the output voltage of the generator. Yeah. So this output voltage of the generator can then be controlled or adjusted, and therefore the speed of the motor, of the DC motor, can then be controlled as well. Okay, and the function of if you look at this part here, this is the field circuit of the DC motor. We can also then use this to control the speed of the motor, as we will see on the next slide. Okay, this slide we are going to skip. Yeah. This is just another example of a Ward-Leonard system, and you can visit the site and read the article in that on that website. Okay, the speed can be adjusted above the base speed by reducing the motor's field current. Yeah. So if you see it here, the motor field current is the one that is can be controlled by changing the resistance in the field circuit of the DC motor. Yeah. So we can cover a wider range of speed by combining the two, i.e. by changing the field current of the DC generator, one, and secondly by changing the field current of the DC motor. Yeah, field current of the generator and field current of the DC motor. Okay, and then if the field current of the generator is reversed, then the motor's direction will also reverse. Yeah, so this is a nice feature. How you can change the direction of the rotation of the DC motor, i.e. by reversing the field current in the generator. The system can also regenerate, i.e. it returns the machine's energy of the motion back to the supply lines. If heavy load is first raised and then lowered by the DC generator, yeah, when the load is falling, then the DC motor will act as a generator. Yeah. And so this DC motor, or more accurately, is now become a DC generator, is producing voltage, and then this voltage will then be supplied to the next machine to it, which was the DC generator, but now it's behaving as a motor, and then it will then supply the motion to the AC motor, and which is now behaving as a AC generator, and then it will then be able to produce three-phase voltage as its output. Yeah, this is the when the DC machine is running in the regenerate mode. Okay, what are the disadvantages of this Ward-Leonard system? I think it's quite clear that it requires 3 machines of about equal rating. Yeah, so instead of 1, you end up with 3 machines. Yeah, so you can imagine the complexity and also the size. Yeah, or the volume, and then how that it will take extra space as well. Yeah. And by having the 3 machines, it will further reduce the system efficiencies, because the total efficiencies will be efficiency 1 times efficiency 2 times efficiency 3. So if you imagine, if let's say if each of them has got efficiency of 90%, so you will end up with efficiency of roughly about 72% only. Yeah, it's okay. This is another disadvantage of the solution. Yeah, the efficiency is reduced quite significantly. Okay, and then due to the disadvantages, then as an alternative, when the technology became available, the solid state solution by using thyristor was then used. Yeah. By having this, it's first reduce the complexity so significantly. It's a lot cheaper. Yeah, it's cheaper to use the solid state components rather than the machines, and the efficiency, the losses can be also reduced significantly. Okay, before we talk about the SCR-based controllers, let's briefly get some introduction on the silicon control rectifier, or this SCR. It's similar to a diode, but it can be controlled. And the symbol also you can see that is pretty much similar to a diode. You've got the anode and cathode, but additionally you have a gate here, the gate that will allow us to control this diode. Okay, like a diode is unidirectional, i.e. it will conduct current in one direction only, i.e. from the anode to cathode. Okay, and it's triggered or switched on by current pulsing going into the gate. Yeah, you can supply pulsing current here to the gate, or by increasing the voltage between the anode and cathode beyond the breakover voltage. So there are 2 different ways of switching on this SCR. And how do you switch it off? To switch off, we can reduce the current through it. So we can reduce the current that goes through this below the holding current. Or with the gate turned off, short circuit the anode and cathode momentarily with a push button switch or transistor across the junction. So we can, when the gate is off, i.e. we don't supply any pulses, then we short circuit this anode and cathode. That's another way of switching off this SCR. Okay, so again, basically this component is like a diode, but it has a gate to allow us to control whether it's allowing current to flow or it's just switch off. So it's just stopping current from flowing. Okay, so the first SCR-based controller is the 2-quadrant SCR-based controller. Okay, and the figure shows us the circuit diagram and the motor. Okay, the average voltage applied to the armature of the motor, yeah, this VA, and therefore the average speed of the motor depends on the fraction of the time the supply voltage is applied to the armature. Yeah. So depends on the fraction of the time. Yeah, we are what we actually do is we have this 3-phase input AC voltage, and then we've got this ACR which will rectify, but the rectification is done on time with some timely basis. This ACR will be switched on and off, and the ratio of the on and off will define the output voltage. The longer it's on, it means the higher the voltage. The longer it's off, or they are off, then the lower the voltage. So if we vary this ratio, then we can then adjust the armature voltage of the motor. Okay. However, this particular circuit is only capable of supplying an armature voltage with one polarity, which is this will always be positive relative to this point here. Okay, so the top one here will always be positive relative to the bottom one here. However, we can still reverse the direction of the rotation of the motor. How do we do that? We do that by reversing the magnetic field, and we reverse the magnetic field by reversing the direction of the field current. The field current of the motor, if it is reversed, then the motor will also reverse in its direction. So this means that if we remember the 4-quadrant Cartesian, then this motor or this machine can run here, quadrant 1 and quadrant 2, where the torques and speeds are in the same, both of them are in the same direction. Okay, and then notice that it is not possible for an armature current to flow out the positive terminal of this motor, since current cannot flow backward through an SCR. If you imagine here, if you look at the diagram again, the positive side, if current cannot flow in this direction, because of the way the SCR works is unidirectional, it will only allow current to flow, in this case upward, if the SCRs are on. Okay, so it will allow the current to flow in the other direction, and therefore the motor cannot regenerate. Even if it's generating some voltage, the SCR will block the voltage, so they will not reach to the input of the system. So it means that it is not functioning in quadrants 2 and 4. It's only operating in quadrants 1 and 3. So only motors, and you don't have the regenerating mode, so it cannot behaving as a generator. Okay, this slide shows us the rectifying process. So from the 3-phase AC voltages, then you will get this as the VA after the rectification. Okay, and the next one is Okay, now as you can see, so yeah, this 4-quadrant solid state DC motor controller it's got more functionalities. It allows the motor to regenerate, which can be a very useful feature in many applications. However, the downside is, compared to the 2-quadrant, you have to add additional components that will add some cost to the solution. These solutions, both the 2-quadrant and the 4-quadrant ACR-based motor controller, are significantly cheaper than the Wardianot, resulting in a lot more efficient solution as well. Okay, and you can this slide here shows us how we can reverse the direction of rotation of DC motor. We can either reverse it by using the armature connections, or we can also achieve it by using the shunt and series field connections. Yeah. So the first figure on the left hand side, yeah, figure A, is showing us the motor when it's running in its initial direction. Yeah. It can be clockwise or counterclockwise. Yeah. And for the second one, yeah, we reverse the direction by changing the armature connections. Yeah, this is the armature connections of the motor. So instead of initially it was going in this ways, we just switch, yeah, the connections, so it becomes crossing over like what we see in this second figure here. Yeah. So by changing this, by switching over these connections, the motor will then run in the opposite direction. Another way of achieving it is by changing the connections of the field, yeah, the field circuits. Yeah. In some motors you've got only the shunt. In some other motors you've got only the field, yeah, field winding. Yeah. In some other motors, which is the compounded one, and then you have both. Yeah. So by using these field circuits, we can also change the direction of the motor. Yeah, similarly, just like in the first method, here we just basically switching over the connections. Yeah. If you got only, if it is a series DC motor, then you will only have this, so you can reverse this connection. If you got the shunt, then you can just reverse this connections. Yeah, just like illustrated in this illustration. Okay, so again, for changing the direction of a DC motor, you can either reverse the armature connection, or you can also reverse the field connections. Now the final part is, how do we stop a DC motor? Okay, how do we stop a rotating motor? Should we just stop the supply voltage? Yeah? Or is it going to work if you just stop the power supply? Yes, the motor will stop eventually, but we have to wait a bit longer. Yeah? Especially if the motor is coupled to a heavy inertial load. Yeah? Because of the inertia, then the system tends to keep its speed. Yeah? So the speed is dying down over some time. Yeah? It will not stop immediately. And there are two methods to actively stop a DC motor, which is by using what we call as dynamic braking or plugging. We are going to discuss this in the following slides, and we'll see which one will stop the motor fastest, yeah? i.e. just switching it off, or by using this dynamic braking, or by using plugging. Okay, this first slide shows us this dynamic braking, yeah, the first active method. Okay, to illustrate this, first assume that the motor is running normally, and the connection can be seen from figure 1. So the motor is running normally. You supply some voltage here and across the motor, yeah, and the motor will then rotate, yeah. Okay. Okay, the first method is called coasting. Before we come to the dynamic braking, the coasting, which means that number 2 here, yeah. Here we just open the switches basically. So we open the switches and we disconnect the motor from the power supply. Yeah. So the motor is now disconnected from the power supply. The motor will continue to turn, but its speed will drop due to friction and windage, and induced voltage continue to exist, falling at the same rate at the speed. Yeah. So you got some induced voltage across this, and it's linear or proportional to the speed. Yeah. So as the speed is lowering down, the voltage is also lowering down, but it takes time before the speed reaches 0. Okay, and then the third one is dynamic braking. The illustration is illustration number 3 on the right hand side. What will happen here, if you see the connection, yeah, originally it was, if you see this one, connected to the power supply. Then we switch it over, so that now the motor is connected to a resistor instead. Yeah. When the motor is connected to the resistor, because of the speed, it has some EMF, or the internal generated voltage, across this, yeah, across the motor. This will become positive and negative. So current will flow. Yeah, current will flow in the here in the clockwise direction. Okay, so current will flow in this direction. Previously, when it was running, if you look at on the left hand side, the figure on the left hand side, the current actually flows through the motor from the top to the bottom, i.e. downward. But now the current is flowing upward. Yeah, compare the figure 1 and figure 3. In figure 1, the current is flowing downward. In the figure 3, the current is flowing upwards in the motor. Okay, and this means that the torque is reversed. Yeah, the torque produced by the motor is reversed, and because the torque is reversed, it's actually in the second state here in the illustration number 3. During the dynamic braking, the torque produced by the motor is actually in the opposite direction to the direction of its rotation. Yeah, let's say if it was running clockwise, then here the torque is if the speed is clockwise, the torque is counterclockwise. Yeah, so that as an effect, the torque will decelerate the motor, and it will decelerate faster than if you compare to the coasting one, because in the coasting one it's just the friction that will slow down the motor. But now, in addition to this, the friction, you also have an active, if you like, an active torque given by the motor to stop it, to slow it down a lot faster than before. And again, it's by using this external resistor and then connecting the motor through the resistors instead of the power supply. Okay, that's the dynamic braking. Yeah?